In this video, I will help you review how to use calculus to solve non-uniform engineering problems. For example, if we want to calculate area of a rectangle shape, then we know that its area is x times y, because we know y doesn't change with x. However, if y changes with x, in the second example, so y equals x to the power 2, and then the problem becomes difficult. So calculus provides a powerful tool to deal with problems where variables change with time or location or other reference variables. The idea of calculus is to cut the total area into small regular elements, which is called differentiation, and then in second step add up all elements, called integration. Here, to solve this problem, we first cut the total area into 10 regular rectangle elements, and then later we add them up to obtain total area. You can tell that the accuracy is not satisfactory, well, because n we use here is 10. By changing n, we expect that the error will be reduced. So in this video, here we change the total number of elements into 100, and this time you can tell that the error decreased significantly, but still we can see some error there. Well, if we cut into 10,000 elements or 1,000 elements, the error becomes negligible. And in general, we know that if we have infinite element, the error will be completely eliminated. As a matter of fact, differentiation does use infinite number of elements. And we'll see that how to use differentiation to get a small element. Now, to solve the problem, and we'll use two steps. The first step is we arbitrarily choose a point on x coordinate, and we use a variable location x to denote its location. Second step, and from point x, we extend x by dx, and the dx is infinitesimal small. In this way, we'll get infinite number of elements. Then we create a small rectangle element with dimension dx and the other dimension y. Y here is x squared. The area of the small elements equals y times dx. Once we have the small area, and we can add up all small elements by integration. So a equals integral dA, and dA replaced by y dx, and then x squared dx. X will start from 0 to 2. By evaluating this integration, we'll obtain the total area as 8 divided by 3. Now, to help you better understand this problem, we look at a double integral problem. Now, in this case, we have a mesh surface. The height of the surface in a coordinate z equals r squared. R here is a radius in a polar coordinate. The problem is to calculate the volume formed between the mesh surface and the horizontal surface. Again, we'll use two steps to solve the problem. In differentiation, we arbitrarily choose a point, this time on the horizontal surface, and we'll use polar coordinate on the horizontal surface. So the variable to denote the location will be r, radius, theta, angle. To better visualize it, we'll look at the top surface. So on top view, and then we extend r by dr, and then extend theta by d theta. In that way, we'll form a small area. That small area with one length, dr, and the other length is r times d theta. Then we extrude this dA up until it meets the measured surface. Then the height of the small volume will be dz. Then we can calculate the small volume dV equals height times area, dA equals r cubic, and then d theta dr. Once we have the small volume, and then we can sum them up by integration. The total volume equals integral of dV, small volume, and then plug dV into it. And this time, there's a double integral. We have r and theta, two independent variables. And we know r will start from 0 to 1, and theta start from 0 to 2 pi. By evaluating this integral, double integral, we'll get pi over 2. Right, so up to this point, we finish these two problems, and the takeaway message is by reviewing calculus, you will see that calculus is such a powerful tool that can deal with problems with irregular or non-uniform physical properties. And you will see that how to apply calculus in fluid problems later.